Meeting started and meet all. Hello, good morning, everybody.
Morning.
Morning.
We are still in the, we have a bit of few minutes to start, and thank you for attending. I'm gonna mute you all, not because I don't want you to talk, but because I want to avoid noise. And accept. We will start the meeting at 9 and probably 2-3 minutes, just to give a bit of time for everybody to join. Meet.
Sampai ke 12.
Hello, I'm Ed.
Hello, hi.
Hello. Just a few minutes before we start.
Yeah.
And guess what? When this thing goes global, somebody,
Hi, John.
somebody else is going to be the global distributor for those.
So, looks a bit rude. I have to mute everybody. All right, now it's almost 9, so a few more minutes. Normally, some people join a few minutes later. You can keep the camera on if you like. I like to talk to someone instead of talking to myself. Very good. So now it's 11. Let's wait a few extra minutes. Starting. A lot of people coming. All right, so good morning, everybody. So I'm just waiting a few extra minutes to give a bit of time for the people that are running late to join, and then we start. I'm gonna keep you all muted, so we try to reduce the background noise and hopefully we increase the experience for everybody. But at the end of the session, we will have a 15 minutes where we can actually answer questions, so you can unmute yourself and ask a direct question. All right, one more minute. All right, so I would say we start. Good morning, everybody. So my name is Luca Garagnani, and I'm here today with Enrico from Prismian, and we are going to discuss about demystifying partial discharge. So the purpose of this webinar is to introduce the concept of partial discharge. So I will not go too deep into the analytical side and the theory behind. I'm gonna try to talk on a easy way for everybody to understand, even the people that are new to the concept. And at the end of our presentation, we will have Enrico presenting a case study. But just running through here. So first, a bit of introduction. My name is Luca Garagnani, and I'm a Chief Operating Officer for Machine Monitor in the department called Op Monitor. So a few years ago, we started developing some analytical tools to move toward the...
Anyway, not today.
Sorry? Sorry, I need to mute all, so we avoid noise. And in Machine Monitor, I've been responsible for conducting partial discharge testing and on different assets, in particular rotating machines, cable, transformers. And today I'm gonna be the host and the presenter of this webinar, and I'm gonna talk about partial discharge. Together with me, there is Enrico Borsari. If you want to introduce yourself, Enrico.
Morning, everyone. My name is Enrico. I am based in Singapore, where Prismian Group has a sort of regional headquarter for the services that provides in the Asia Pacific Oceania region. I look after the service business, as mentioned, service business as in preventive maintenance, partial discharge based service business. Thank you, Luca.
Very good. All right. So today what we will talk about, as I mentioned earlier, so today is going to be an introduction about partial discharge, and we need to start with the basics. So try to define what is a partial discharge, and I hope it's not going to be too boring for people that already are familiar with this subject. Then I'm gonna show some effect of partial discharge on asset. And I think the best way to show how the PD affect the asset is to show actually some picture of evidence of this discharge detected. And then I'm gonna try to introduce the concept of what we should do. Obviously, we have only 1 hour, so I don't have time to explain any specific case, what we do in case we have this type of discharge, what we do in case we detect discharge on this type of asset, but I'm gonna show a general concept of when we do partial discharge and what is the purpose of doing the test and what we try to achieve when we do the test. And that all hopefully should help to understand what we should do when we detect this type of problems. And at the end, we will have a real case study presented by Enrico using the Prismian technology. I try to be within 45 minutes, and after that, we will leave you 15 minutes to ask your questions. And please, in the meantime, if you have questions during the presentation, just add your question to the Q&A section. So at the end, I will go through all the questions, and eventually we can have a live interaction, so you can unmute yourself and have a real conversation. I would ask everybody to mute themselves if the system didn't mute automatically, just to try to minimize the noise in the room. All right, so let's start with the basics. So what is a partial discharge? So this is a question that all new engineers, especially that they are not familiar with the subject, that they need to, or they are engaged to do this type of tests or to analyze some data, they ask, what is a partial discharge? So the name can be a bit misleading because there is the discharge and partial, and maybe it's not so obvious to everybody. And I think the best way, instead of reading the complex definition that we have in the standard, that for me, non-English native is very confused, I prefer to show a picture. Right, so in this slide, we have this picture. I don't know if you see, can you see my cursor? Can you see it, Enrico?
Yes, I can. I can.
Very good. All right, so in this picture, we can see an example of a real partial discharge. You can see this overhead line where we have this set of insulators, and this is the corona ring, and this obviously is the high voltage wire, right? So this corona ring is subjected to extra high voltage, and we can see that we have some spark in the air surrounding the corona ring. In particular, this spark is localized where we have a sharp point, right? And this is a partial discharge, is a localized discharge in the insulation system. In this case, our insulation system for this picture, for this overhead line, is the air surrounding the conductor. So all the air around the conductor is the insulation. And in some condition, if we exceed the electric strength of the air insulation surrounding the conductors, you will have the discharge of the air localized to where we have a very high stress. And you can see very well. So we have some spark here, all around the corona ring, and also here in this location. So in this location, we would have a very high electrical field capable of ionate the air. This is a very easy way to understand what is a partial discharge. Obviously, it's an electrical discharge, but it's only partially affecting the insulation. We can also use a different representation and try to represent a classic insulation system that we are more familiar with, like if you have a cable, a rotating machines, a switchboard, right? All these systems, they have a conductor, obviously, which is the conductor that carry the current, and we have a low voltage electrode, which is the ground. Between the high voltage and the ground, we have an insulation system, an electrical insulation system. In the previous picture was the air that isolate the wire to the ground. In cable could be a solid insulation like XLPE. In a rotating machine is a complex system of paper impregnated. In a transformer is a combination of paper and oil, right? So we have different electrical insulation system, but all of them, they have the same purpose. They need to isolate the conductor, which is in high voltage, to the ground, which is a zero potential. Obviously, in the ideal case, you would expect to have a perfect and continuous insulation system, but in reality, we have some small defects. So all the insulation systems come with some defect due to the manufacturing process. Could be very small or could be a bit bigger, depend on the type of asset that we are talking about. Like cables normally has a very microscopic voids, and the insulation is tested in the factory to try to eliminate from the market cable with big defect that can trigger this type of discharges in a live condition. But rotating machines are popular and famous for partial discharge, right? In rotating machine equipment, where we have impregnated insulation, we expect to have a bit bigger void and partial discharge in a normal condition, because this manufacturing defect can be quite big. This is an example, and obviously as example, I'm going to use the rotating machines where it's easy to see this type of defect, while in the cables or transformers may not occur so often. In rotating machines, we can see this, and you can see very well in this picture where we have the copper, which is the conductor. The black material here is the slot coating, which is the ground electrode, and in between we have the insulation system composed by many layers of paper impregnated, and you can see that there are still some empty spaces, and these spaces are the microvoids that are left during the manufacturing process. And they may be critical or less critical. They can trigger discharge or not trigger discharge depending on how big they are and in which location they are, these voids. If you take the example of rotating machines, coils close to the start point will have zero potential, so there will be no enough voltage in this location to generate a discharge, but void close to the terminals where we have the full voltage of the winding may be triggering discharges. We also have other type of discharges that may be generated by aging, and normally that is the case for old asset that has been in operation for quite some time and they are reaching their lifetime. This void can become bigger, and the reason why this void become bigger is because obviously the material, the insulation material, become more brittle. So the thermal and mechanical stress that the insulation can be subjected to can basically increase the size of these cavities. And the bigger the size of the cavities, the smaller the electrical field required to trigger the discharge. Let me see if there are, okay, they're all into the room. Other defect, which could be due to installation, can cause partial discharge. And in this example, I show a picture of a cable termination 3-core, where we can see actually the evidence of the discharge. So obviously this is an installation issue, right? So the two phases, they were very close each other and almost touching in a place where there is no low voltage electrode. So the low voltage electrode is ended here, and all here is only insulation. So we don't have the ground electrode, we don't have the screen, and in this location you should keep some space to avoid this discharge. And this is an example to show that partial discharge can also be caused by a wrong installation. And in most of the cases, when we talk about stationary assets like cable, transformers, switch, the discharges are actually caused by installation problems. To go more a bit in the literature and to better represent the discharge, we know that we have different names. And if you are familiar with PD testing, you may have seen some report. You can see that someone talk about corona discharge, surface discharge, internal discharge, interface discharges. And sometimes we give names based on the asset. Like you can talk about slot discharge for rotating machines, stress gradient discharge still for rotating machines. But they are all groupable and represented by three main categories, right? So internal discharge means all the discharges that occur due to defect within the insulation. So the electrical discharge is into the insulation system and is not visible from outside. Surface discharge are discharges that are on the surface of the insulation. And in this example, this is another picture of rotating machines where we can see the bar leaving the stator. And let me try to get the cursor. I cannot. Okay, so I try to represent. Here we have the stator, here we have the bar, and you can see this plasma that is only present from this line, looks like has been drawn, right, like a paint. And this is due to the manufacturing defect. So obviously the slot coating is ended here, so the zero potential is here. After that, we have the high voltage, right? And to mitigate the transaction between zero potential, which is the slot coating, and the high voltage, which is the bar without screen, there must be a grading system, which is a semiconductive layer, right? That should be overlapping the slot coating to make the contact with the zero potential and expand in the bar to mitigate the surface stress. So we need to reduce the voltage on the surface of this bar. If the layer is not installed properly, like you can see here, probably is this line, and there is a gap existing between the slot coating and the stress grading, you basically have 50% of the voltage of the bar in few millimeters of surface. So that causes obviously a discharge on the surface of the bar. And this is a very common surface discharge. And we will see in the presentation, the same problem can be found in cable termination, bushings. So it's a very common issue. Corona discharge are all the discharges that are originated in the high voltage connections. And this type of discharges can be critical for the asset, like if you have a corona discharge in a closed cabinet, that can create a lot of ozone and over time can corrode the materials. But if it's in an open environment, like in this picture on the overhead line, the corona discharge is not a problem. For when we do the test and when we do the analysis, more a disturbance. How do we move from those pictures to something that we can actually detect and analyze? So all the partial discharge are detected using oscilloscopes. So we use oscilloscopes very fast, and we try to detect the pulses generated by this spark. And you can see in this picture an example of one partial discharge detected with an instrument that is an ultra-wideband instrument with ultra-wideband. Ultra-wideband means a bandwidth that is larger than 1 megahertz. In this case was a 30 megahertz instrument. And you can see here the pulse of the discharge, and you can see how fast is this signal. So you talk about few nanoseconds of event. and these represent only one discharge, right? So how do we understand if we have a discharge just by looking this pulse, and how do we understand what type of discharge we have by looking these pulses? Because as you can imagine, the pulses may look very similar between corona, surface, and discharge. It's the same phenomenon, and maybe slightly different the pulse, but still is a pulse. So how do we understand if it's a discharge and what type of discharge is it? We correlate the pulses with the applied phase-to-ground voltage. As I showed in the previous slide, so the partial discharge are always, in most of the cases, generated by the phase-to-ground voltage. So we have the voltage applied to the main insulation, which is a phase-to-ground. If exceed the dielectric strength of the air within the defect, can trigger and spark this spark. So in our analysis, we always correlate this pulse with the phase-to-ground voltage applied to the asset we are testing or to the phase we are testing. Obviously, there are cases where we can have phase-to-phase discharge, like the picture I show between the two cores of the three core, but that are different cases. But the analysis is done in the same. So we correlate our pulses with the phase-to-ground voltage synchronized with one of the phase. How the graph is built: if you take any PD instrument and you do the measurement, you will actually see a graph where we have the sine waveform and many dots. How this graph is built: so the instrument, as I say, try to correlate the pulses, the high frequency pulses of the discharge with the applied phase-to-ground voltage. So we have our phase-to-ground voltage, so we connect to our instrument a signal that is related to one of the phase-to-ground voltage of the system under test. And obviously, that represents the applied voltage. When that applied voltage exceeds the inception voltage for this particular defect, and that means that the electrical stress into this small defect exceed the dielectric strength of the air insulation, we have the first spark. And this spark is very fast, only occur for a few nanoseconds, right? Our sine waveform is 20 milliseconds at 50 Hertz. So obviously, this pulse is detected, and what the oscilloscope does is going to measure the amplitude, and is going to locate the pulse as a dot in this graph in the exact right phase position with the same amplitude. Obviously, the voltage in the system is as a sine wave, so it's going to keep growing and decreasing, and we can reach the inception condition also on the negative semicycle, and in this case, the pulse is going to be negative and exactly the same. But this graph, if you only take a 20 millisecond acquisition, would not be enough for us to do the analysis because we have only few pulses. So during the PD measurement, we try to record multiple periods of the applied voltage, and we collect multiple pulses. So the process repeats, and we acquire more pulses, and we actually arrive to a picture where we have several thousand of pulses, and we analyze this graph. This is the graph that is popular for partial discharge detection and is called phase resolved PD pattern, which is exactly built as I show. So our oscilloscope is correlating all the high frequency pulses detected generated by the discharge that are detected with specific sensors with the applied phase-to-ground voltage. And this graph contains a lot of information. So this sine wave represents the phase-to-ground voltage of the system. And if we synchronize properly our oscilloscope with the right phase, we actually have the pulses of the discharge positioned in the right phase position for the phase under test. The amplitude, which can be millivolt or picocoulomb, and here is important to understand the difference between millivolt and picocoulomb. Today, we don't have time to enter too much in the details, and I'm gonna post in the chat a link to a book that is a theoretical book, and you can read about and explain very well the difference between the bandwidth and the difference between the instrument, and also give some advice on how to test the different assets. I'm gonna post the link later. But the main difference between millivolt and picocoulomb that I think is very important to understand is that all the instrument measure in millivolt, right? We are using an oscilloscope and we are measuring a voltage output, which is the output of one transducer, which could be an high frequency current transformer, a voltage divider. So our measurement is in millivolt. We talk about picocoulomb if we can correlate the millivolt with a known charge, picocoulomb, that we physically inject into the system. So that make clear that obviously when we do online testing, unless you do a calibration, you're not able to measure in picocoulomb. And most of the instruments that we use on site, they are designed in a frequency bandwidth which is too wide and would not allow you to have a linear correlation between millivolt and picocoulomb at the different frequency. So normally when we work on site, we only measure millivolt. When we do offline testing and we utilize instruments that offer a frequency bandwidth below 1 megahertz, which is a very small bandwidth for partial discharge measurement, we can talk about picocoulomb. And that you can see also by looking the standard. So for most of the assets like cable, transformer, we have specific standard that talk about how much should be the picocoulomb in that asset in the factory, right? They do the factory test and they need to reach a certain criteria of picocoulomb. Obviously, in the lab, they're going to have an instrument which is limited in bandwidth, but that offer the possibility to properly correlate millivolt to picocoulomb in a reliable way. When we are on site, our instruments are designed to operate with the site condition, which is noise. So the instruments are designed to eliminate noise, and to do that, we need a large bandwidth. So we work in millivolt. Sorry for the long digression, but it is an important topic that most of the time is very confused. And obviously, we can see the phase. We can also see the intensity. All the color here represent how many pulses we have in the same phase and amplitude position. Each type of discharge will have a specific graph, right? We will have a graph that represents internal PD, a graph that represents corona PD, a graph that represents surface PD. And what I want to try to pass today as a message is that the graph is important, but when we do the test, is not the only analysis that we do, right? Because this PD pattern, especially when we work in a live system where we have multiple signals detected at the same time, may look confused and not very easy to distinguish, like in this case, a perfect sine wave. So I will show later in the presentation, but the PD pattern analysis is important, but is not the only way you analyze the data. So we try first to understand where is it, and then we try to identify what is the cause by analyzing the graph. I hope I'm not going too fast, and please feel free to add question and we will answer the question at the end. All right, so now just to show you all these partial discharge, this physical phenomenon that we can detect, but what's happening if we don't detect and if we don't do anything, right? How they affect the asset. And I think the best way to express this is to show the consequences of not doing any test at all and let the asset operative, right? And you can see here this picture, there is a medium voltage termination, is a 33 kV cable termination in a wind farm, and you can see the failure, right? This termination blow up in this position. If you understand about the construction of the cable termination, you can actually understand why it failed in this position. So you can see here very well that the jacket of the cable has been cut here, and you can see very well that there is a bit of bump here, right? So here is where the semiconductive layer, which is the screen of the XLPE insulation, is cut. And after that, we have only XLPE insulation. So this is actually the same location where I showed a picture before of a rotating machine, stator bar, where you can see the discharge, right? In this case, we had probably the same problems. The stress gradient system, which should decrease the surface stress in the transition between zero potential on the semicon and full potential on the XLPE, has not been done properly, which could be they forgot to put it, or they didn't put enough material, they left accidentally an empty space, and that will trigger a constant discharge on the surface of the XLPE between the semicon and the XLPE. And that will be a constant discharge that is there repetitively when the cable is energized. Obviously, this discharge is not going to fail the system immediately, but it will fail the system eventually. And that you can see the consequences. So would that be preventable? Yes. If they would have done the test during the installation process, we may have probably been able to see this defect. And if they would have done the test anytime during the operation of the cable, we would have seen this problem, right, before the failure. This is a very common failure for cable, and this is another cable. 33 kV, different termination. This is for GIS switchboard connection. So it's a plug-in termination, but exactly the same. We have a failure in this location, and in this case, they actually open the cable, and we can actually see the discharge evidence. You can see the white line here. This is obviously a discharge that was occurring in this location because there was no grading system. And no grading system means you have electrical voltage line coming out here and generate a voltage stress on the surface of the XLPE that generate discharge. Different picture, different problem. So I don't talk only about this surface discharge into the termination that, by the way, we call interface, just to confuse a bit more. And is a mix between surface and internal. So we call interface. And this is a picture of a gas air insulated switchboard system, 33 kV in New Zealand. And you can actually see some white dust here in this location. And the white dust is the evidence that they had a discharge in this cabinet. This discharge can be due to a defect on this insulation, could be due to contamination dust, and once it triggers, it will eventually tracking, will create a tracking, and it will eventually fail this system. But what it also does, generate a lot of ozone. This discharge is affecting the air of the cabinet, and since it's a closed cabinet, the air is limited and doesn't circulate, so all the air will be contaminated by ozone, and having high concentration of ozone with humidity will create acid. When you have acid, then you start to have corrosion, and you can see all the components into this cabinet are corroded. The spout is corroded, the bar is corroded, so there is obviously a consequence of this discharge. Would that be detectable? Yes. From the moment the signal is triggered, any PD detector would detect this surface discharge. Different asset. This one is a rotating machines, as you can see, where we can see the stator winding, and we can see this beautiful evidence of the effect of the partial discharge. You can see the bars into the slot, and you can see that some bars are black and some bars are white. The real color should be black, right? Black is the semiconductive layer called slot coating that is supposed to ground the bar, but not completely grounded in order to avoid to short the lamination of the core. If this material is too resistive, it will build up a very high potential across this little gap. And this high potential will be the highest in correspondence of the high voltage coils. And you can see very well here. Starting from here, we start to have discharges that eroded over time all the slot coating, and all the high voltage bar is gone, the coating. What is this? Is a manufacturing issue. Obviously, the coating selected and the air gap was not compatible and generate this discharge. Another picture of our rotating machines where we can see the effect left over of the surface discharge on the grading system. And exactly the same, we can see a perfect line where you see the slot coating transition between the slot coating and the bar without screen. And in this case as well, there was an issue with the grading system that create this white mark. What they create, these discharges, a huge amount of ozone. What the ozone create with the humidity? Acid. And as a consequence, you will have a situation like this. This is a terminal box of a motor, I think, where you can see all the corrosion effect. Every component into the box is corroded. And this is a consequence of the presence of discharges. So just to summarize, which is, I think, is very important, the partial discharge are the result of defect that you have within your electrical insulation system. So are never the cause of the defect. They are always an effect that come out due to the presence of a defect, and that defect is in a position where you have, in certain condition, an electrical stress that exceed the dielectric strength of the air insulation, and that create discharge. The discharge tend to grow over time, as you can see from the previous picture of the slot discharge, right, where all the coating material was gone. Obviously, at the beginning was very tiny, the discharge, but if the defect grow, the discharge grow. We will have higher discharges, faster discharges that we call repetition. So the number of pulses generated per each cycle of the applied voltage increase. And that is a direct consequence of the defect getting worse. So the worse the defect, the higher the amplitude of your discharge. Do we have threshold? Not really, not for all the application, and it's not always applicable to have a criteria based on the threshold. And the failure that I show in the picture is always a consequences of a combination of events. It is never the partial discharge that failed the system, but is the combination of an over stress that arrive in a weak point of the electrical insulation system. So the partial discharge is gonna affect the characteristic of the insulation in that specific point, and is gonna decrease the dielectric characteristic of that electrical insulation system. And once an overstress, which can be caused by the normal operation of your asset or by a lighting or whatever happened in the network, that overstress as an overvoltage can reach that point and fail the system. So this is very important because most of the time we have been asked, okay, this is the discharge, how long my asset is going to last? Unfortunately, we don't know. It's unpredictable, and we don't know when you're going to have the combination of this effect. And I try to accelerate, otherwise I don't finish on time. All right, so what should we do about having discharge? I try to express this concept by using this classic curve, the PF curve, right, where we represent the asset condition over time. And we can see in this case that the asset has a certain condition for a long period of time, and then eventually a potential failure trigger, and the condition deteriorate until we have the failure. And this is called PF interval. Our partial discharge obviously is the potential failure that can be triggered in some condition. And once we have it, if it's stable in the system, it can eventually fail the system. Again, do we know how long it takes between the inception to the failure? So do we know prior how long is the PF interval? No, no one will be able to tell you, right? But we can focus on what we know, right? If we do a proper commissioning, that is when we do the test, we try to have exactly this graph. So if we do the proper commissioning, we make sure that the asset has no existing defect. This is slightly different for machines, but let's talk about assets where they don't have normally discharges, like cable, transformer, and switch. Commissioning tests should prevent you to have problems. During the life of the system, I call proactive monitoring. There are many technology nowadays available to do a continuous monitoring, spot testing, that give you the possibility to detect if there is a problem into the system. But most of the people focus on reactive monitoring. So once they know they have a problem, then they are going to do something. And obviously, this is a reaction. So you know you have a problem and you try to understand what is going to happen. How can we use our PD measurement on our advantage? So in this phase, we are going to do testing, which could be a continuous monitoring, spot testing, online testing, offline testing, depending on your strategy and your condition. But the purpose of this is to be able to detect the problems, localize, and identify what is the problem. And you want to be able to detect the problem as soon as practically possible, because the sooner you detect the problem, the more time you have before the failure to take action. Once we detect the discharge, we need to be able to pay more attention to it and try to monitor it and try to determine, is the condition stable or is getting worse? We want to try to determine if the defect is getting bigger or not, right? And that is not to avoid the failure indefinitely, because one day it's going to fail, but is to give the site and the owner of the asset time to plan an action to repair. So you need to repair the asset to try to avoid the failure. If you don't do anything, that is going to be your PF interval. If we properly detect and monitor this phenomenon, we avoid the failure, we are able to run over again with the PF curve and have another curve. Obviously, in this example, I represent like the condition didn't improve after repair. And in this case, let's say we have another event happening after some time. We detect again, we try to repair again, and eventually fail, right? Even if you do this cycle only once, you will expand the life of your asset. And this is the way the condition monitoring, in particular for this partial discharge, can be very effective and can avoid failure and expand the life of the asset. I hope it's clear. And now I'm gonna give the word to Enrico, which is gonna go through this case study and is gonna show you exactly what I tried to explain. We need to detect, identify, and try to detect the problem before it fails. Over to you, Enrico.
Thank you, Luca. So if I need to go to the next slide, I can ask you, or I will just ask you. You're muted, yes. Luca. Okay.
Yeah, you can ask me.
Okay. So first of all, thank you everyone for attending this short webinar. As mentioned by Luca, what we will try to do now is to show you the one of the tools that Prismian uses, as well as a success case that we got out of the use. So Luca, maybe we can go to the next slide. The device that we use when we perform site spot services is called Precam Portable. Is the device that you see to your left. The device is basically a electromagnetic ultra wideband antenna. How do we use the device? As you can see from the right side of this slide, we place the device on the cable next to the accessory that we want to monitor, and we remotely control the device via iPad. Prismian created an application, proprietary application that can connect and communicate with our own portable device. So just to clarify, we place the device on the cable. The cable has to be seen as our access point to the system that we want to monitor. It's not that we are monitoring that exact spot on the cable. We are actually trying to get an insight on the accessory that says before and after the cable, the location where the device was placed. Luca, you can go to the next slide, please. Okay, so now we'll try to define a bit, characterize a bit the ultra wideband antenna. We are gonna give, I'm gonna give you some ideas of characterization based on a, let's say, user experience point of view. First of all, the device, let's talk about the sensitivity of the device. So when we go on site, when I go on site, I need to have a device that is as sensitive as possible. We discussed, Luca discussed previously the difference between picocoulomb and millivolt. So when we use the device on site, of course, we focus on millivolt. The result is in millivolt, but to characterize the device, this device has been characterized in test condition, and it has been characterized in picocoulomb. So this device is as sensitive as low as 0.5 picocoulomb, which is the sensitivity that we want to have. Of course, on-site conditions might be different, but it's good to have a starting point. I mean, as a starting point, it's good to have a very good sensitivity. We also have to remember that the device that we use is an antenna. So sensitivity is somehow related to the directionality, let's put it that way, of the device. So there's a direct connection between sensitivity and distance from the source of the discharge that we want to from the object that we want to monitor. The closer I get to the device, the higher is the, let's put it that way, the amplitude that of the signal that I can get out of the test object. The further I move away, the lower will be the signal. This seems to be a drawback at first, but it's actually very useful in test situations. We use the device in a way that we call survey mode. So we screen a cable accessory after accessory, and we try to determine which accessory brings the higher energy content, the higher amplitude, and by placing the device next to the source of the discharge, then we get higher amplitude from that location, and we are able to reject. We are able to use the device, the noise immunity capability of the device, because what else is coming from elsewhere will be naturally reduced in amplitude. The device has a flat bandwidth. So Luca spoke about oscilloscopes before. This device is a device that does not resonate. So there's no resonant behavior. There's no behavior of the sensor that get mixed with the waveform of the partial discharge that we want to monitor. That means that the reconstruction of the partial discharge pulse can be done to, let's say, a higher accuracy than standards, and that allows us to use the waveform as a tool to cluster noise, partial discharge, different events, and to differentiate one from the other. So the device is a device that has this, let's call it, waveform clustering approach. Eventually, last but not least, cloud platform. Whenever we have doubts on our measurements carried out on site, we simply feed the measurement to a cloud platform. Again, that was built around this sensor, and for this purpose, the cloud platform gives us a reply on the severity of the and on the type of the partial discharge that we found on site. So this was a bit the main features of the device. If you go to the next slide, Luca, I will try to explain very briefly that the device is not a device that is meant for a specific type of or a specific asset. It's a device that we use all across the medium voltage and high voltage electric assets. So we start, of course, from the obvious outdoor insulated air insulated terminations, joints, transformers monitoring, and GIS monitoring. All of these assets are assets that we can monitor with our device with the very same approach I mentioned to you at the very beginning. So by placing the device on the cable next to the accessory that I want to monitor. We'll jump now in this next 5 minutes to leave some space for Q&A to the cases. So one case that we want to bring to you is a case that we had in Queensland. So Luca, you can go directly to next slide. Actually, you can jump this slide and you can go to the next one. We were called by a customer to perform a spot measurement activity. The purpose of the activity was the one to determine whether there were assets that could have failed in the short time, and whether we could have been able to identify partial discharge during, let's say, on certain assets. So in this case, the target was a transformer, and the activity conducted on the transformer was to monitor the primary side of the transformer, the secondary side of the transformer, and the transformer tank. You can see a picture of the secondary side to the left and primary side to the right. As you can see, on the secondary side, we have 22 kilovolt terminations. I believe we had a total of 12 of them. And the way we perform the measurement in that case is exactly the same as before. So cable after cable, we would put the device next to the termination, and we would try to get signal out of it. The next slide shows us what was the finding for 11 out of the 12 terminations that we monitored. 11 terminations were showing just noise and magnetic saturation. So you can see the noise as a flat distribution of pulses in our PRPD or phase to ground voltage graph, as Luca mentioned at the beginning. And you see at certain intervals, at certain phase angles, some straight lines. These straight lines are our magnetic saturation. On the next slide, we'll show what was found on one out of the 12 terminations. And this is the one in red. There's a cluster in red, and the cluster in red is representing a potential partial discharge. At that time, we had to do some study on it, but today we can tell you that this was a clear partial discharge. As you can see, there are symmetries between the two clusters. There's also a cluster to the very left that we didn't highlight in red, but there are symmetries, and there is a certain level of phase angle alignment with the applied phase to ground voltage cycle there. So this was a clear partial discharge that was found on this termination. We made a bit of study on this cluster, and if we go to the next slide, you will see the PD waveform of that specific partial discharge together with the energy content. As you can see, with this PD waveform, the PD waveform shows two opposite peaks. The cable, the distance between the transformer and the switchgear was very short, and the partial discharge was let's put it that way, bouncing between the two ends. That's why you have two positive and negative peaks. The diagnosis of this discharge, what could this discharge be? Luca, if you go to the next slide, our assessment was this is an interface partial discharge. As Luca mentioned before, we have normally three type of partial discharge, but to complicate things, sometimes we like to define discharges that are in between all these three groups. This is exactly one case. This is an interface discharge. It's an interface that by observing the cable system, it's internal, but it's internal at the interface between two, let's put it that way, components. So it's an interface, it's a discharge that was between the cable and the termination. A discharge that has something to do with the preparation of the cable or the preparation of the termination or the termination process. Our technician said this is most likely due to mastic degradation. Speaking to Luca, the opinion is more or less shared. It's either mastic degradation or a wrong use of mastic or wrong use of gradient during the installation. This was the assessment, and this prevented the discharge to, let's say, manifest itself. If Luca, you can go to the next slide. A mastic degradation ends all the time with a failure. There's no way of, as Luca was mentioning, a PD will always grow stronger and more energetic. It will not reverse. So mastic degradation create these sort of issues. Wrong installation can create this issue. In general, partial discharge will never go back to make our termination healthy. It will only degrade it. So as you can see, we have in these two pictures the same failure happening over and over again on three different set of terminations. You have the orange one to the left, and you have the red failures on the right. So in a nutshell, I think the message from our side is we always try to push for preventive maintenance way before the PF curve or into the PF curve, but we always try as Prysmian to conduct preventive maintenance rather than reactive maintenance. So increase the reliability and the life of the asset before the PD become an obvious failure. I think that's it from my end, Luca. I don't know if we have questions.
Very good. I think now we can open for questions. Very good case, Enrico. Let me try to stop sharing so I can share ourselves so we can all see each other. No, but I'm sharing. I do this and then I do this. Here we go. All right. So we have some questions I see in the chat, starting from the beginning. So Julius, hi Luca, from the previous PD pattern, what the difference between the two frequency signals detected by the PD? And now it's difficult to know which one. Julius, can you please unmute yourself and say exactly
what I mean there, Luca,
Yeah.
is that because I'm just new with this PD testing, and I just wanted to know, because we don't normally analyze the report that we do, so we normally send it to you guys and you do the review. So I just wanted to know basically what's the meaning of those two frequency signals from the top and the bottom. Are they the noise, or that's what I mean?
Okay. So let me try to take the pictures and try to talk over. So you refer to, I don't know if you were seeing this one, right?
That's correct. Yep.
All right. So basically, all these pulses represent individual discharges, and when we collect the discharges over a applied phase to ground voltage, you can see that you have discharges that occur during the positive semicycle and discharges that occur during the negative semicycle, and this is actually a defect. And by analyzing this graph, we can characterize the signal and say, okay, we have a symmetry. Like Enrico was saying, is symmetric, so we have positive and negative discharges occurring in the right phase position. And in this case, since the amplitude is symmetric and we have a sine wave representation of this shape of multiple pulses, we can say that this is a void, so it's internal discharges. So this pulses actually represent the discharge itself. And by analyzing this picture, we can say what type of discharge is it.
Okay, thanks for that, Luca.
No worries. Thank you so much for attending and for asking questions. All right, next question. Afiz. Hi, Luca. What's the difference of PD testing at different ISC frequencies? 100 to 400 kilohertz or at 10 megahertz? All right, so this is a very good question, and that is come back to the discussion millivolt and picocoulomb. And I know when we do field testing, this is a hot topic. So most of the instrument that you can find in the market, they also offer the possibility to measure in picocoulomb, and you need to be careful to utilize that functionality properly. So when we talk about the picocoulomb measurement, we want to work in the IC, and the IC standard does not give you a specific frequency. It does not say, oh, you need to have 10 to 20 kilohertz. No, it gives you a frequency range. So you can have some system that they work in a narrow band and some system that they work in a wide band. I don't remember out of my head exactly the frequencies, but they give you basically a range of frequency in which you can apply this correlation between millivolt and picocoulomb. And most of them, they have preset frequency range. So when it comes to 100 to 400 kilohertz, maybe that specific instrument utilize that frequency range to do the correlation millivolt and picocoulomb and work in IC compliant standard. When we work at 10 megahertz, is normally a ultra wide band. If it's the same instrument that you're talking about, that means that instrument allow you also to work in a bandwidth that is wider than the IC standard. And most of the time, this device they do because they want you to be able to further analyze the waveform and being able to filter. And most of the time we use for noise rejection. So each device that you can have, they are designed for specific application and they customize the bandwidth that they use in order to be able to apply their tools for noise rejection. Did that answer your question, Afiz? Yes? I can see there is one more question, and this time is for Enrico. When you say move away, do you mean the device on the cable or the iPad?
The device on the cable. So the device has, it's an unconventional PD measurement device. So for instance, let me try to explain by giving an example. It doesn't have to be clamped to any ground connection. For a cable that is exposed, but even for a cable that is buried with accessories exposed or with link boxes accessible, you can screen through your cable and through your accessories by placing the device on the different accessory, one after the other. At the end of your campaign, you will be able to compare what's the, let's simplify, amplitude that you retrieved from any accessory, and you will be able to pinpoint the source of the PD using this relative analysis. The iPad from the pre-cam can be 30 meters, 40 meters away, and that's a given.
And there is a follow-up question. What prompted this test on the transformer in your case study? Was there an issue before or a normal routine?
Yeah, there was a history of failures, and the customer wanted to see whether wanted to make an assessment on whether preventive maintenance tools and habits could prevent these faults. By showing that we were able to detect a partial discharge, we were able to demonstrate that yes, preventive maintenance is the way forward, at least for this type of discharges. Lead the way before they become fault.
Hi, Enrica, this is Sydney from NG. When you said, when you said failure, was this a cable failure or the transformer was failing?
Termination failure.
Termination failure. All right, thank you.
And I see, Sydney, you have a question also to me after. What is the connection between measuring the cable and conducting PD testing? So
yes, I'm asking this because we have some sites where, if you look at some of our sites at Melbourne, where we have 6 transformers being paralleled together with 33 kV cables. So my question for this is, we sometimes measure these cables when we finish a routine job, and there's no commissioning test in terms of PD discharge. So I just want to know what the connection is, measuring and doing a PD test. What do you reckon? What's your recommendation?
Yeah, so that is a great question. So measuring normally is basically applying a DC voltage for 1 minute and make sure that the insulation is not too bad and you can energize it. So normally measuring doesn't give you much value in terms of diagnostics information. It will just show you that the insulation can be energized at high voltage normally. So when we talk about PD testing, we do more diagnostic investigation. So you detect the presence of possible defects. So it's slightly different. I know for commissioning, especially medium voltage, PD test is not mandatory, and most of the site they do withstand test after the measuring, and they just let the cable apply with an overvoltage for some time, and if it doesn't fail, it pass. But that doesn't prevent you from having problem into the termination that you will only see during the life of the cable. So my recommendation is if you talk about cable that are rated above 11 kV, normally 33 kV is very critical. It's better you do a proper commissioning with some diagnostic information like PD and tan delta that will give you a better picture of the cable.
So this is where I ask Enrico a question. Enrico, is this what you provide? Are you an external contractor, or is this provided by Machine Monitor?
It depends. It depends on what you need. Prysmian is a producer of tools. So Prysmian is the owner and producer of the precam that you saw in the presentation. Machine Monitor provides services with its own or with other brands tools. So it's a matter of what you need. If you need a product or if you need a service, basically.
Yeah, Machine Monitor obviously is we are local to Australia. We have several branches in different states, and we do this test. So we do all these condition assessment tests and all over Australia. So if you need some help, just send me an email and I can see how can we help you.
Yeah, we work with Machine Monitor. I'm just trying to. I've not seen the device before. That's what I'm asking.
No, that's good.
Yeah.
Very good. Thank you so much for the questions. So we move on. Thank you for the questions. There are a few more questions. Yes.
I have a question, Luca.
Who is talking? I'm a bit.
It's Rocky here. Can I ask a question?
Hi, Rocky. Yes, I can see you have the hand up.
Right. I think this question is for both Enrico and you. It's pretty clear from the photos that we do have a lot of failures occur at the transition point between the cable semiconductor tape and the stress control tubes. So obviously there's an issue here of the stress control method. Do you know of any new technology, or is Prysmian actually have a much better termination kit?
That's a good question.
Because we are trying to detect the PD, but where I'm coming from, I wanted to stop the PD. Obviously, especially for the 33 kV cable, right? Now, if you don't reduce the discharge increase the discharge extension voltage, then you're going to get that you ionize the air around it, and then you create a surface PD.
That is correct.
Any recommendation on that? I mean, I know you guys are selling this partial discharge monitoring, but it's also good to know what's the actual cure.
Luca, let me say, Prysmian also sells accessories, has a long tradition of manufacturing accessories. So PD and accessories, I mean, partial discharge tools and accessories doesn't exactly go hand in hand in Prysmian for the reason that you just mentioned, because one tried to make accessories that never failed, the other one tried to find failures in accessories. The only thing that I can say is it's very difficult to ask your question, Rocky, when you say what does Prysmian have that the others don't. I don't know in terms of accessories. I can only tell you that in terms of accessories, we have a long experience in cold shrink, and Prysmian thinks that cold shrink has much more benefits than heat shrink. So the only thing that I can say is that if you have a lot of experience with heat shrink and you don't find yourself satisfied with heat shrink and failures that arise from heat shrink, you might be willing to try and move into cold shrink. Then I leave you the assessment of which brand is better in terms of cold shrink to yourself, but this probably is an idea.
And then obviously, Rocky, after you install, if you do some testing, before energizing. That would prevent the problem at all.
Sorry, guys. My lines kept being cutting out, so I didn't actually hear anything what you said. So that's all right.
Oh.
Issues with
basically,
with the line, with the connection.
Yeah.
So because I'm currently working from home, and
I think
I didn't hear any of that.
we can come back to you
I'll
by
give you
mail.
guys a call.
Yeah,
I'll give you
exactly.
guys
Yes,
a call because
yes,
I'm also
yeah.
interested with this online monitoring.
Yeah, very good. So we talk shortly. We just finished the
Thank
question.
you.
I saw there are many questions. Thank you, Rocky. So, John?
Yeah, am I online now? Not muted?
Yes.
Yeah.
Yes.
Hi, guys. Look, I'm John Pemberton. I'm one of the directors and co-owner of Machine Monitor. And I'd just like to thank you for being on this webinar. I think it's been great. And thank you very much, Enrico, for joining with Luca. A really, really nice, informative presentation, I must say, with great examples from the field. And sort of while I've just got the floor here, I would really like to encourage sort of any of you guys to come to the Machines Conference, which is in June. It's in mid-June. It's at the Melbourne Convention Centre. It's held in conjunction with Australian Energy Week, which is a huge conference. It's the leading energy conference in Australia, and all the utilities attend that conference. Many of the CEOs will be there. And Machines is Machine Monitor's traditional conference that we've actually run for, this is the 22nd conference, over 22 years. So, but now it's hosted by Quest Events, and it's hosted as a stream of Australian Energy Week. So we'll have a stand there, and it's a very technical conference. And a lot of these sort of, Luca will be speaking at the conference, and our rotating machine expert, Ron Scully, he'll be speaking too, and other very, very high level speakers in regards to, particularly in regards to condition monitoring of stationary and rotating assets, mission critical electrical HV stuff. So yeah, encourage you to look for that. I did post a link to it on the meeting chat, but all you have to do is just Google Machines 2024, all one word, Machines 2024, and it will come up. 2-day conference.
Yeah, thank you, John. Yeah,
thank you very much.
I was about to invite you too. So if you want to come, I want to be there, and I'm going to present a solution for online testing as well. So if you want to have a chat about PD testing, just join the conference and we will meet there. Just to finish the questions, I see there is a question from Lambert Daniel. Hi, Daniel. Are you still with us?
Hello. Yeah, I'm still here.
Hi, Daniel. How are you?
Yeah, thanks for the presentation today. I learned a few extra things that I hadn't heard before, so thank you.
Very good. So I see you have a question, and this is for Enrico. Does the PRICAM get used for commissioning of cables?
Yes. Yes, it's again a device that you use on site. So if by commissioning you mean HVAC, nowadays a bit of MVAC, yes, of course, it's not the ideal device that you should use for your routine test in the factory to commission the cable to the standards, if this is what you mean. But for on-site commissionings, yes.
Yeah, so is this included in the 24-hour soak test? Let's say if we did a 24-hour soak test, we can put this unit on and see if our terminations are good. Is that right?
Exactly.
Okay. All right. Thank you.
Welcome.
Very good. Thank you so much for the question. And we have Kalpesh. Does PRICAM locate PD on transformer? Kalpesh,
yes.
are you still with us? Maybe left.
Well, let me reply in broad terms. Yes, what we can do is we can locate whether the discharge is in the tank or on the primary side, secondary side. When I say primary side, secondary side, I mean terminations. And the exact location inside the tank, this is something that we cannot provide.
Very good. And then another question for the PRICAM from Hamad. Does the PRICAM comes with ultrasound detector?
No. It's we are not a ultrasound product provider, so all that you need is in the pre-cam itself.
Very good. Let's see if we have some more questions. All right, so there is one. Thank you for the link, Mustafa. So why PD pattern and voltage have different polarity in the first slide you show? Oh, that is a great question. I don't know if you can still see here. So can you see my slide? Yes. Can you all see my slide? I guess so. Yes. Oh, very good. All right. So the polarity that can be like in this case where we have a positive sine wave and the negative discharges, or in the previous slide probably was opposite, like in this case. That is determined by the sensor you use, and everything comes to the measurement circuit we are using. So if we want to represent easily, so if this is your insulation system, which could be the cable or the rotating machines insulation, which we can call C insulation. When we measure the discharge, we can either use a divider, which is connected in parallel, like this is a capacitive divider for a rotating machines application, for example, or we can use a current transformer, which is like this, CT. Both the device, both the sensor, they have a polarity, right? So the polarity is obviously the way you measure the voltage on the sensor, which is from here to ground, from here to ground. That is how the sensor measures in the oscilloscope. And if we correlate the polarity with the physical propagation of the discharge, you know that if you have a discharge in this insulation, this discharge will travel as a current through the ground and back into the high capacitive path, which we show a low impedance path for the current, and go back to the source. So basically your PD is a current generator in high frequency. And you can see that if you use a CT, the polarity of the high frequency current, the polarity of the PD, and the polarity of the sensor, they match, and we normally call direct measurement. So you will see a PD that looks like this in the graph if you synchronize properly. But if you use a capacitive sensor, so a divider connected in parallel to your insulation, we will have opposite polarity, and we call indirect measurement circuit, and your sensor measure with the reverse polarity. So when we test machines, you will always find the graph that are opposite compared to the applied voltage. When we test cable, it depends where the current is flowing to. Is flowing out of the cable or into the cable, you will see different position. Did I answer your question? Very good. All right, so I think we ran a bit longer, and thank you for the great questions. And it was a great session, and I hope you enjoy. And we see you all in June in Melbourne. Thank you so much.
Thank you. Thank you, Luca.
Thanks.